Okay, so it's a pleasure to introduce the first speaker of today, Basak Gürel from Florida. She will talk about the Hofer-Zehnder and multiplicity conjectures for dynamically convex Reeb flows.
Okay, so thanks very much for the invitation. It's a pleasure to be here as always. I just realized that for me, we're celebrating 20 years here, right? So for me, it's the 10th year anniversary happens to be. Okay, so it's a pleasure to be here. So I'm going to talk to you today about our joint work with Erman Çinili from ETH and Victor Ginsburg, who is here, about the multiplicity and Hofer-Zehnder conjectures for dynamically convex Reeb flows. Okay, so the setting of the question is the standard contact sphere. So Reeb flows on the boundary of star-shaped domains in R2N. So here the notation I'll try to stick to for this, P dot will be the set of uniterated simple closed Reeb orbits, so to speak. So prime closed Reeb orbits. So we're going to be interested in the multiplicity problem for such orbits in higher dimensions, in dimensions essentially of interest in dimensions greater or equal to 5. So there are, of course, lots of things you can ask about these things. The number of them, infinite, finite, any threshold number, type of orbits, or a certain phenomenon happening in the presence of a certain type of orbit, etc. So there are lots of questions one can ask. It's an old question, of course, going back to the work of Lyapunov, but lots of results by a lot of people like Moser, Weinstein, Rabinowitz, of course, Eklund. And here's this conjecture. Maybe exactly pretty much the same way it was stated in a paper by Leonardo and Miguel. So let's write it, let's call it the N or infinity conjecture. So split into two parts intentionally. One part talks about multiplicity, the other part talks about the so-called, now we came to call this a Hofer-Zehnder conjecture. That the number of prime closed orbits is at least n on 2n minus 1 dimensional sphere, standard contact sphere. And the Hofer-Zehnder part is about n or infinity. So if this number is greater than n, then there must be infinitely many simple closed Reeb orbits. So it's, of course, the way it is stated, it's a very general statement, and we are nowhere near kind of proving something like that with no assumption. In dimensions, again, higher than greater or equal to 5. So again, this first part goes back to like this Eklund. The second part, it's the reason why it's called Hofer-Zehnder conjecture is one can view this as a higher dimensional Reeb variant of the well-known 2R infinity theorem of Frank's that Vincent told us yesterday, reminded us. Okay, of course, there is at least one orbit that goes back to Rabinowitz. And then before that, there was Weinstein for convex hypersurfaces. And then, of course, we much more generally, we know that the Weinstein conjecture holds for the standard contact sphere. So then we know that there is at least one. We also know that this number n in the conjecture is sharp because we have non-degenerate irrational ellipsoids have non-degenerate Reeb flows with precisely n simple closed Reeb orbits. And then with this in mind, we can also turn this into, I don't know, okay, I can get it inside. Okay. A statement about Reeb pseudorotations. So Reeb pseudorotation for Reeb flows for me for this talk, for this work, means that you have just finitely many prime closed orbits, uniterated closed orbits. So then one can state the Hofer-Zehnder, Reeb Hofer-Zehnder conjecture as if this number is finite, then the number is precisely n. Okay? So Reeb pseudorotations, possibly rare, but they are interesting objects. There are ergodic pseudorotations going back to all the way to the work of Katok in the 70s. And then what do we know? Well, in higher dimensions, we know beyond, like, past the Einstein conjecture, there's one. We know basically nothing in the generality that I have written here. If you don't assume some conditions, some index condition or some non-degeneracy assumption. So we don't know if you have more than one, for example, even for S5. Okay, so that conveniently brings us to the very common convexity condition. This is a more general condition than strict convexity, which we know is not preserved under symplectomorphisms, contactomorphisms. So the condition, what came to be referred to as dynamical convexity, was introduced by Hofer, Wysowski, and Zehnder. It's an index condition which says that, again, I'm on S2n minus 1, that the Collins-Zehnder index of closed Reeb orbits is at least n plus 1. So now, throughout the talk, whenever there is no non-degeneracy assumption in the picture, mu minus, mu plus will refer to respectively lower and upper semi-continuous extensions of the Collins-Zehnder indices. So then this is mu minus, basically. There is no non-degeneracy assumption here. Yes, various comments here maybe are due. Strict convexity implies dynamical convexity, but not the other way around. Also, maybe it makes sense to note that in the condition, this n is kind of, it's important, it's half the dimension of the domain. So we have, like, I and Victor, Leonardo and Miguel, Gutenkang, we have all results. If, you know, what happens if you can prove results under different kind of, you can replace this by some other number, but then what you get is a different thing. So if this number is less than n, you may get fewer orbits. If it's greater than n, then you don't have examples, etc. So n is actually important here. And then if one wants to think of this in the context of some other situations, some other manifolds, etc., this is just, one should keep in mind that you can define it, but then you will never satisfy the condition unless this homology, positive symplectic homology, is 0. Okay? And then finally, you can make sense of it, of course, for unit disk bundles, cotangent bundles. Then it can also be phrased as a curvature condition. So this is the dynamical convexity. So here are the results. So this condition will also be essential is essential in this work as well. So the first theorem is the following. If the contact form is dynamically convex in the sense I have just described, then you have at least n prime closed Reeb orbits. So the important thing here is that there is no non-degeneracy condition in this theorem. I will go through some sort of previous results. So it's known if you don't assume this, if you assume non-degeneracy. So now what else can we say? So now this is true as it is with no non-degeneracy. But if you assume non-degeneracy, and if you assume that you have a pseudo-rotation, then one can say more. So you can say that there are precisely n non-alternating orbits, and that you may have more orbits. If you have more, then they must be definitely alternating. Okay? Also, you can also say about the index parity, etc. These are all important things, of course, to know about your periodic orbits because they all register differently in symplectic homology or equivariant symplectic homology, etc. So again, this notion is going to be coming up. So alternating, non-alternating is just about these indices will have, when it's in the non-degenerate case, this just means that this index parity stays the same throughout the iterations. Okay? Okay, so no questions? Okay, so the next result, so the first one maybe is mainly in the realm of the multiplicity part of the story, and the second one is more in the dichotomy, n or infinity dichotomy part of the story. And this result is, here we do need to assume non-degeneracy, and moreover we also need to assume that the domain is centrally symmetric, so M is minus M, everything is in Rn. Then we have this n or infinity dichotomy. Sort of, we can be much more precise in that way. And if you have n, then again we have more information about the simple closed Reeb orbits. They're symmetric, and all of them are non-alternating. Okay. Any questions about the results? So that's that. So some history of the question. Dimension 3 is, of course, a very special dimension. Here we have very powerful tools, ECH machinery, global surface of sections. We have heard yesterday from Vincent a good review of the results that are known in 3D, and in particular for the standard 3 sphere, we know everything about all the conjectures I've written down, and one even knows more. So not just for the sphere, but other closed 3 manifolds as well. And of course, there are lots of people who worked on these problems. So when you go to higher dimensions, of course, the story becomes a very different story. Number one reason being the fact that you just don't have anymore all these nice tools. So hence, essentially, almost every result has some kind of a convexity or non-degeneracy assumption there. And if you want to also change your contact manifold, you would expect that all these lower bounds do in general depend on the manifold itself. Okay, so not just the dimension as well. So as I already said, these questions are rather elementary. What we don't know is very basic here. Is at this level, we don't even know if there is more than one in general and more than 2 in the non-degenerate case. So now lower bounds. So this is the multiplicity story. So what we knew is that if we assume some index condition, so back when I defined dynamical convexity, in fact, nowadays one can also get away with slightly lesser condition than dynamical convexity. And so this is why I'm saying DC type conditions here. Together with non-degeneracy, it was known that we have at least n. Now you remove non-degeneracy, this bound immediately drops down to n half. And again, I will briefly remind us how this proof works, then it will be clear how you get down to half of n. And then there are various other results like Wang, long school mainly, so much more precise, like in dimension 4, 6, 8, etc. One can say things in this range. So there are a lot of credits here going back to Long and Zhu's work, and then Liu, Wang, Hu, Gutan Kang, of course, Macarini, Abru, and Victor and I worked on these problems a little bit, so there's a lot of history here. And then there is also the side of the story in the more like Conley conjecture type situations where you may expect like unconditional existence of infinitely many. Again, Victor, Leonardo, and I worked on this question as well at some point. Then you can also ask the questions from like generic existence perspective. We know some here too. So, for instance, Reeb flows on the standard sphere generically have infinitely many going back to Viterbo in '89. This is, I think, resonance relations is the main thing here. So, the history of the HC conjecture, of course, the main history here is the Hamiltonian case of the conjecture, starting with, so this is now Hamiltonian closed symplectic manifold, Hamiltonian diffeomorphisms. So, it goes back to Frank's theorem that for S2, the number of periodic points is 2 or infinity. What's known as the 2 or infinity theorem. And then this was, there was the conjecture in Hofer-Zehnder's book for CPN that this number is n plus 1 or infinity. Of course, the number coming from Arnold, the lower bound coming from Arnold's conjecture. And then this, Igor essentially proved this conjecture, even for a broader class of closed symplectic manifolds. And a main tool here was a Smith inequality. And this goes back to the work of Seidel, and then it was developed further by Shelukin and Zhao. And we also have this conjecture now for like other manifolds, like compact toric manifolds, work of Bai and Xu, different proof by Simon Allais. So we know a lot more in the Hamiltonian case nowadays. But there was essentially nothing in the Reeb case, if you wish, till recently. So there is yet another sort of kind of sort of perspective on these things. One can also view HC conjecture from a different perspective. That's maybe what I'd like to call forced existence of infinitely many. So this is the perspective that if there is some periodic orbit in the picture which is not needed for some reason, so homological, geometrical, whatever reason, for example, non-contractible orbits for Hamiltonian diffeomorphisms, for example, then this is maybe the reason for the existence of infinitely many. So you can definitely view the Hofer-Zehnder conjecture in this context, for example. And then we have some results in this, various results under these conditions, again, going back to works of Allais, Marta, our work, and other people. Now, the following theorem that goes back 10 years, what one may think of is the, what we think of is maybe perhaps the first result in the Reeb HZ direction. So this theorem said that for CPN, if you have one hyperbolic orbit, then you have infinitely many. Now let's move on to the Reeb HZ conjecture. So I say that, we essentially didn't know anything about this dichotomy before 2023. So what, except for again some upper bounds from Leonardo and Miguel's work for lacunary Reeb flows, so that means that Conley-Zehnder indices have the same parity for all closed Reeb orbits, for the sphere, for instance. So the theorem that, together with Arman, Victor, and Marco, dating 2 years ago, we proved that on the standard contact sphere, if you assume again in the dynamically convex case, if the Reeb flow has one hyperbolic closed orbit, then you in fact have infinitely many orbits. This is just literally the sort of analog of the CPN result in the Reeb case, and so this is maybe what I would think of is maybe the first result in the HZ direction here, but more maybe in the direction of forced existence of periodic orbits. So again, no non-degeneracy here, and this DC is actually much weaker than DC in the actual theorem. And interestingly, again, the results I stated at the beginning of my talk, the subject of today's talk, are really independent from this one, and the techniques of proofs are different as well. So it's like substantially different theorems, even though they may sound kind of similar. Okay, so now let me tell you a little bit about our approach to the whole thing. So this is a bunch of such, this is just to set notation a little bit, so one doesn't need to really seriously read this. This background assumption is just the fact that the closed orbits are isolated. This is just to ensure that, you know, the relevant persistence homology, we have the relevant persistence homology all good, but it's totally kind of expository assumption here. So this is going to denote the filtered symplectic homology groups. This is an action interval. And so you will see this T here in the talk from this point on. This refers to this filtered homology. So, of course, I'm lucky that Victor reminded us all of this story yesterday. And we know that in the non-degenerate case, this is generated by one generator coming from the domain, star-shaped domain. This is regarded as degree n action 0, and then for each closed Reeb orbit with action less than t, we have two generators with precisely opposite parity orbits with the same action. So this is going to be the symplectic homology persistence module. Exactly like Victor defined yesterday, and however, in my case, I will need them to be graded vector spaces. And CH, so this is over any field, CH will be the equivariant local homology, so equivariant homology over Q. So CH will always be over Q. Okay, so what's the strategy of the proof? So first of all, in essentially the rest of all the theorems, please do keep in mind that I'm going to assume that the Reeb flow is a pseudo-rotation. In other words, there are finitely many periodic orbits in the picture. And you will see me reminding you repeatedly this assumption. So the strategies of the proof is the following. So it's rather simple. It's that, well, we do know that all known Reeb pseudo-rotations are actually either irrational ellipsoids or they come from them via the conjugation method. And so the idea is basically that, and also they're all dynamically convex, they're all non-degenerate. This is the known, this all pseudo-rotations we know. So the idea is to compare a general dynamically convex Reeb pseudo-rotation on the standard sphere with the symplectic homology persistence module of the irrational ellipsoid, and show that they look the same, basically. Okay. So, in fact, when you add some a resonance condition into the picture, we can also show that if you give me a dynamically convex Reeb pseudo-rotation, there is always a matching irrational ellipsoid with precisely the same fixed point data. Okay? But keeping in mind that they can have, of course, very different dynamics, sort of. So we cannot tell them apart by looking at the symplectic homology groups. So here's the picture of ellipsoid. Again, this is exactly the picture that Victor described us yesterday. A non-degenerate irrational ellipsoids. These are the indices. They are lined up in this increasing order, and that this ratio of the action to the mean index is constant, and that through every real number t, or for all t, let me at this stage say it this way, the dimension of SHT is precisely 1. So through every real number t, there is 1 bar passing through that from the language of persistence modules. So here is this picture. So we have this ascending staircase pattern here. So this theorem underlies the whole kind of argument, the main theorem, and it tells us that in the general case, the picture is exactly like that of ellipsoid. So for every t and for every field f, the dimension of symplectic homology, t filters, let's call it this way, symplectic homology is 1. Okay, so now again, it would be, for our purposes, it would be fine to have this theorem for Q, but in fact, the proof goes through, has to go through positive characteristics. So, and then you get the result for every F through universal coefficient theorem, basically. So this is the main result. Okay, so now this theorem, so let me once more go back. Again, we have a DC Reeb pseudo-rotation. Under these conditions, we have this result. This theorem has some important consequences. So here's some more terminology. Let me denote by P of F, or just simply by P, is an orbit which we call F visible. It just means that the symplectic homology, local symplectic, non-equivariant symplectic homology is non-zero. In fact, it would be, I think, assumed that just they are eventually visible, but let's, for the sake of today, just suppose that X is F visible. Then you have, of course, I mean, you can kind of try to see how you can possibly test this, how you can relate visibility of X, the visibility of X to the K, which kind of an important separate matter. And then the support of this local homology is the collection of degrees where this is going to be non-zero. You can also similarly define the support for the equivariant local homology. So it lies in between mu minus and mu plus 1. So here's this corollary of the theorem. Again, you have a dynamically convex Reeb pseudo-rotation. So the first consequence is that all F visible orbits have distinct periods, and the dimension of symplectic homology, local symplectic homology, is precisely 2. And that in the second part we have Q coefficients, and this is supported in 2 consecutive degrees. This is denoted by HH plus 1. And the equivariant homology is supported in precisely H, and otherwise it is 0. This is, again, the same story as the ellipsoid, the irrational ellipsoid, literally. So this, again, this is directly related to what happens in the Geisen sequence, which connects equivariant and non-equivariant homology, etc. So the second part of this theorem, at least for the time being, it's only true for Q coefficients. Okay. Now, what does this? So this is actually not difficult to see. For instance, if you had like two orbits with the same action, you would immediately get that this symplectic homology. Remember, the assertion of the theorem is, let me go back for a second, says that this dimension is 1. If you had two distinct orbits in the same, with the same action, you would immediately get that this dimension is to be at least 2, for example. So the corollary D is a rather immediate consequence of this. Let me go back here. And then this one then will follow from the Geisel sequence, like this fact, basically, that we have this direct sum here. Okay, so what does this buy us? So this buys us, again, remembering that there is no non-degeneracy condition in the picture, this buys us a degree. Basically, I can then use this H, precisely the degree where the equivalent homology is non-zero. I am going to take a visible orbit. Again, let me emphasize that it's only defined for a dynamically convex Reeb pseudo-rotation and when the orbit is Q visible. So then we can associate it to a degree. Which would be the Cohen-Zehnder index if things were non-degenerate, obviously. So now the next theorem is kind of the sort of a bridge between the theorem C, corollary D, and the actual results. So what this is going to tell us, again, we're in the setting of theorem C, so DC pseudo-rotation on the standard contact sphere. This is the Q visible orbits, and this is the symplectic homology barcode over Q, as I have introduced. So we have the following two things. So the degree map, this is this H map here. There you go. So this map is a bijection to n minus 1 plus 2n. And orbits with larger degree have larger index, larger action. And then there is also the other degree map. This one is the map from the barcode. So given a bar has a degree to it. Again, this comes from the structure theorem that when you write your persistence homology as a direct sum of interval modules, like Victor explained yesterday. So there will be just this one degree. If this bar is present in the barcode, there will be a local homology where it comes from. So, so the first one is defined only in this setting. The second one is a general thing. So this is a bijection. Again, bars with larger degree have larger action. And then the second part of the theorem says that this ratio of action to mean indices is constant. So all orbits, all visible orbits have the same thing, have the same ratio. Okay, so I suppose, I'm not going to say much, but I suppose it's rather easy to believe the existence of such an orbit here, right? This is the one that's going to capture the positive equivalent homology. That's the one that's going to deliver. And then once you have that orbit, then the theorem C is going to tell you that you have like precisely one bar ending at that orbit X and then starting at that orbit X, and then you can argue what this degree has to be in the barcode, and then continue this way. And the second one is essentially a consequence of the fact that infinitely many, so if you have something visible x, there will be like an infinitely many iterations of that orbit which will also be visible, and that infinitely many of these guys will occur as carriers of equivalent capacities, so to speak. This, the second result essentially follows from an argument along these lines, that these ratios are constant. Okay, so now with this in mind, let's try to go through, briefly go through how these theorems work. Maybe the first thing I want to mention is like how we can refine the multiplicity result in the non-degenerate DC case for pseudo-rotations. How this number becomes n, and that n of them are non-alternating. So first, again, underlying all of this is there is a theorem called what we call index recurrence theorem, originally going back to the work of Long and Zhu, which they call it as common jump theorem. So this is going to tell you that there is an index interval. Let me go to the next page maybe. So there will be this index interval from d minus n plus 1 to d plus n minus 1. And then in this index interval, there will be only one iteration for each prime orbit. Only one iteration will occur. And that any other iteration will be outside this range. And then once you have this in mind, this is like an old argument here, discounting argument. And then in this range, you notice that there are precisely n integer points with parity n plus 1. And then you also have, again, spectral invariance non-zero that has to be picked up on these orbits. So you must have at least n of them. And one thing I forgot to say, that the index recurrence theorem allows you to actually pick this d is the shift amount. You can pick this d to be even, all these iterations to be even, and using this you can also argue that immediately that these orbits must be non-alternating. Because the alternating, even iterations of alternating ones will give you zero equivalent homology. So. Now, if you remove degeneracy, non-degeneracy condition from what I've described, this range immediately reduces to n half. So the other half can be occupied with different iterations of the same orbit. So that wouldn't help you more than n half. So now when you use theorem E, and so the orbits with different degrees have different actions, you can then conclude that you must precisely have non-alternating orbits. So that's that part of the story. Now about theorem B, with this in mind, now let me add in the centrally symmetric condition into the picture. In the centrally symmetric case, we have two kinds of orbit, the symmetric ones and the asymmetric ones. Asymmetric ones come in pairs. Symmetric ones are the ones that are invariant under the antipodal involution. But these guys have equal action and degree, and this is impossible by our theorem C or its corollary D. And then everyone has to be symmetric, and this is an older result of Liu, Long, Zhu, and Victor and Leonardo, that every non-degenerate prime symmetric orbit is non-alternating. So you combine everything, and the previous argument I told you that there are precisely non-alternating orbits. So this is kind of rather the older story. So to prove theorem A, again, that's a more complicated story. One really needs to then go into the behavior of symplectic homology equivariant or non-equivariant, and understand the behavior of these guys under iterations of these orbits, and this is complicated even for Q. So, I mean, there are expectations, some conjectures. For instance, you would expect it to be related to the Fuller homology for the return map. Possibly the homology for, say, x to the k is related to the homology for x with some shift of degrees depending on the Hofer-Zehnder indices, etc. But this is a far from being understood situation. Anyway, in our case, the fact that this is supported in 1 degree makes it a bit more tractable. So let me also point out, so this question is kind of, as I said, it's complicated. A lot of things can happen, so you can start with something visible. This can be invisible in a non-trivial way. And we don't know if the converse can happen. You can start with something invisible, and it may start being visible as you iterate the orbit. So these questions, as you may appreciate in the multiplicity business, is kind of tricky and important things to understand, actually. Now, an implication of the whole story is this ellipsoid comparison that maybe I briefly mentioned in the beginning. So with this in mind, one can ask like how similar a Reeb pseudo-rotation is in fact to an irrational ellipsoid. We have this result. So basically, if you have in the scenario where theorem B holds in this case, so I mean there are conditions there. If you add in one more condition that this ratio of mean indices are distinct mod Z, then you can show that there is in fact a matching unique irrational ellipsoid. So then, of course, all orbits are elliptic, etc. Again, the dynamics can be very different. So you won't be able to tell them apart by symplectic homology persistence module. So this theorem actually, there are lots of assumptions, etc., etc. But you know, this theorem actually uses the whole package. So all theorems that I stated gets used, plus Viterbo resonance relations, etc. So to make this conclusion. Again, just like Victor mentioned yesterday, one question here, obviously symplectic homology is not going to help us tell them apart. But in fact, one can ask maybe the proper question is, does interior carry any more information about dynamics, basically, than symplectic homology, anything? Okay, so let me try to explain a bit of the ingredients of the proof. So a bit the proof. So proof of theorem C, so dimension of SHT is 1 for every T. So there are 3 ingredients of the theorem. The first one is the boundary depth upper bound. So basically, if you have the total symplectic homology 0, such as the case, our case, basically, if you, in general, if you have a displaceable domain, omega hat is the completion, symplectic completion. In this case, there is an a priori bound on the length of bars. So all bars are going to be finite. This is kind of one important thing. The observation going back to Erie and also proved in Ginsburg-Schoen paper. The second is Smith inequality, as I already mentioned. That was essential in Igor's work on Hamiltonian HC conjecture. So this is this inequality, basically, that the homology, dimension of homology for this p times an interval is at least as much as the symplectic homology that you pick up for an interval. Okay? But this is true for positive characteristic fields. So And then the last part, as I already said, index recurrence resulted already went into action in this multiplicity result in this description. So this is about kind of a more combinatorial number theoretic result. This is not a symplectic result, I think, and goes back to the works of Lagrangian. Right, so it's about recurrence properties of Hofer-Zehnder indices. Of course, we don't know precisely what happens to Hofer-Zehnder indices or other indices under iterations, but this theorem provides us some understanding, and it tells us that if you give me like arbitrarily long index iterations, indices will repeat themselves up to some like common shift. If you give me a finitely many periodic orbits, for example. So now, by now we have more sophisticated versions of the theorem, and for this work we actually, the one we proved incorporates actions and frequency of these index recurrence events. So we have some control over actions, which is needed, and also like how frequent these index recurrence events happen. So now the outline of the proof with this in mind. So this is the main object. I'm trying to show that this is 1, and I'll do this over positive characteristic, and then it will all extend to Q. So the first result is, to do so, I'm going to prove the following proposition, so that there is it says that there is a real sequence CL going to infinity with bounded gap, for which this dimension, for this sequence of real numbers, this dimension is at most 1. So let's see how this is going to be enough for my theorem. So again, this is like double use of Smith inequality here. First, it's that we know that it is at least 1 because Smith inequality tells me this, and if you pick k large enough, this is only going to see the interior of the domain, so it will be 1. And now, in the second part of the story, again, Smith inequality is used here. Okay, for every t, I can find a arbitrarily long action interval such that this dimension dt is less or equal to d tau for every tau in this interval. To do this, you just simply pick, give me a t, you just pick an epsilon which doesn't intersect the spectrum. Again, for a large k, look at this enlarged interval, and then Smith inequality will tell me that this part of the story. And you also have this part of the story. Okay? So tau is in I, tau over p to the k will be here, and if k is big enough, these dimensions will be equal, basically. Again, everything coming from the interior. So, and to conclude, this is a bounded sequence, so if you give me a t, I can find the CLs exactly entering this arbitrary long interval I, and there you go, basically. Greater or equal to 1, less or equal to 1, equal to 1. So how do we go about proposition 1? So to prove proposition 1, we have another proposition. So it says the following. So indeed, I can have a bounded real sequence such that the dimension of symplectic homology, so this dimension of this filtered homology for all these filtrations CL is actually 0 for all degrees which have the same parity as m+1. So to prove this, let's form this Euler characteristic. So now, and then let's observe that in fact this quantity is independent of t. Again, if you pick t small enough, you will only pick up the one coming from the domain. So in fact, it has to be minus 1 to the power n. And then remembering that this DCL, the dimension that I am interested in, is simply the sum of these guys. And now I can use this and this to conclude that. This is just insert the relevant things in the right places and conclude. So we need to prove proposition 2, basically. Okay, so how do we do this? So we go back for a second. So we are trying to prove that we can find this bounded real sequence CL, bounded gap sequence, for which every degree with parity n plus 1 symplectic homology is 0. Okay, so if you give me a bar, so to start the whole thing in the barcode, so I can assign there's a reasonable way to assign an F visible closed orbit to the beginning of the bar and the end of the bar. So this is again not probably hard to kind of guess how this works. Again, if this bar exists in the barcode, there has to be some orbit where the degree of this bar is in the support of the symplectic homology, and then plus 1 is going to be support in Y, and this orbit is going to have action exactly the beginning of the interval, and the end of the bar will be the action on some other orbit. So you prove that, I mean, one can prove that there is a way to do this. So now let's put this in the basket, and then let's go to our F visible orbits. So let's break these F visible orbits into clusters. These clusters are going to be formed by looking at the ratio of action to mean index. And let me also just remind everyone that this ratio is invariant on the iterations of the orbit. Of course, if an iteration happens to be visible, it will be in this PF set, so it will all give you the same ratio. So they will be in kind of iterations of the same orbit will be in the same cluster. Anyway, so we have finitely many clusters because we have the assumption is that we have a pseudo rotation, we have finitely many prime orbits. And then this is just some bookkeeping. Let's label these orbits in this form. So the I here is going to denote the cluster. Of course, you may have iterations, kk prime and jj prime. Jj prime denotes like different orbits in the same cluster. Well, I mean, they will be in the same cluster if just the index I and I prime are the same, so it's like grouping them. And then you prove the following lemma. It's rather, again, easy to believe, which says that if your if your bars start, the first point, the beginning point of your bar is above a certain threshold, then the orbits actually belong to the same cluster. This is, again, not difficult to prove. It essentially follows from the fact that you have this a priori bound on the boundary depth. Okay, so there is this constant k bar. Just to remind, C bar is the upper bound on the largest bar, and then this is this k bar coming yet another constant from this lemma. So now I'm almost done. So when you combine index recurrence theorem together with the dynamical convexity, the index recurrence theorem in the way that is proved in this paper, namely which has the action controls and the frequency controls of the index recurrence events. So it will tell you that you can find, this is where this, of course, action control comes into the picture. It's going to tell you that there is a bounded gap sequence outside the spectrum, and even integer sequences DIL, such that for all j and k, you have, so remember this YIJKs is my bookkeeping in these orbits, in these clusters and stuff. So if your action happens to be to the left of CL for this bounded gap sequence, mu plus will be here, less than DIL plus m minus 1. And if you're to the right of it, then you will be here. It's in fact an if and only if condition. Okay. All right, so now let's take a bar passing through this bounded gap CL, a member of that real bounded gap sequence. But I want it to be bigger than the C bar plus K bar that came from the boundary depth upper bound and the bound which tells me that there are no intercluster bars. And then let me denote by Yijk is the beginning. Remember in the beginning of this argument I told you that there is a way to assign orbits to the beginning of a bar and the end of a bar. So this is, let's denote Yijk to the beginning of the bar and then Yij prime K prime the end of the bar. Here I's are the same because by this thing I don't have, these bars are in fact happening within the same cluster by my lemma 2. Okay, so then in fact, this is a direct consequence of the fact that you have these, this is the beginning and this is the end of a bar. That follows from the very beginning of this. It's a part of assigning the closed orbit to a beginning and end of a bar. So this is general fact. And now what happens is that these guys, I'm sorry. Happy ending, I'm almost done. Okay, so these guys in fact become equalities, okay? By the virtue of the fact that this Yijk and Yij prime K prime are beginning and end of a bar. So these become, so this difference is precisely 2. And then the degree of this bar is precisely mu plus Yijk plus 1, which is, again, then looking at this thing, this plus 1 is the IL plus n. So it's all like follows from this stuff. Let's remember that DIL are even. So then it tells me that this homology is supported exactly in degrees with the same parity as m plus 1. And this is precisely what I wanted to prove. Okay, I think I'm going to stop here. Thank you.